Myself, Srinivasan from the Department of Mechanical Engineering at Shishan College of Engineering. I'm going to talk about the bias variance trade-off, which is most important topic in machine learning and deep learning. And before going to talk about bias and variance trade-off, and we should understand some certain mathematical representation of data. And when you look at the first order polynomial graph and the data points are scattered and the nonlinear structures. The green one is the function. When we predict using the first order polynomial and that gives a straight line. And when we increase from the first order polynomial to say third order polynomial, it 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 tries to capture most of the data points and generalize the things. And when we increase from third order to ninth order polynomial, and the red one is going passes through all the data points in the data set. So that means it happens to be a overfitted one. Okay, so we increased from third order to ninth order polynomial. So when you look at the first order polynomial, it gives a straight lining equation for the nonlinear data. And I can say this comes under the category of underfitting. When we go for the ninth order polynomial, it is overfitted. So we should have a generalized one. That's what bias and variance trade-off is important in machine learning and deep learning. So let's see what is bias in terms what is bias variance by explaining the things using dartboard. These are come across in our school days and any play game area. So there are four categories I can say. One is low bias and low variance. That is the first category. And if you look at all dots are clustered and at the center of the line, and I get that's why this comes under low bias and low variance. That is the most expected thing for me, common from a person. So if we look at high bias and low variance, and all dots are clustered, but not nearer to the center of the board. So when you look at the third category and all the data points, all the dots are not clustered or scattered and are the near the center of the board. So when you look at the fourth category and all the dots are scattered, not near to the center of the board. So that's why it is comes under the category of high bias and high variance. Okay. So we should have in machine learning model we should balance both bias and variance. So when we talk about model, the complexity increases in both the cases. Well, suppose when you don't have in the first order polynomial, I can say it is underfitting. That model complexity is not it is very model is very simple and the complexity is very less. When you go for the ninth order polynomial and the model complexity is increased, okay, that is because of the bias and variance. And basically model complexity, the term I use in model complexity in machine learning and deep learning is the number of parameters involved in the model and the basis function used in the model as well. Okay, so both the things, both are responsible for the model complexity. Okay. So when we have model and when we go for the prediction, we should balance both bias and variance. Okay, so not only bias and variance, we should look at the error. The error comes from the noise. So mathematically, like I said, the squared bias is basically y hat minus y. Okay, and I can say the bias square is nothing but the expectation value of the squared predicted minus squared difference between predicted and the actual. So the similarly like I can explain the various term as well. Okay. Since we have been talking about the model complexity, because of the parameters involved in the system, and as long as you have less parameters and um, less samples, and you'll end up with more error. So that's the reason the bias time is very high and model complexity is very low. Then the model complexity is keeps on increasing, and we'll end up with large amount of the reduction in the bias and the large amount of variance in the systems. So we should have a point where we should have a point where both are very minimal. That's where we get optimal model complexity. So when we work on machine learning and deep learning, and these are terminology we come across, there is training data set and validation data set and test data set. And based on the most of the data points goes to the category of training data set. And that's where we get the model. And once we get the model, it has to be tested. And it is where we fine tune the hyperparameters in validation data sets. Okay. So once it is done, when we will go for the test, we will go for the testing the model and for the new instant. Okay, so this is a way we have to uh, we have to work on machine learning and deep learning. So when we talk about training error and validation error, and when you have when you have the model complexity is very less, as we have seen in the first category, we'll end up with the high bias. Okay. So when we keep on increase the model complexity, then the training error is going to be very less. But at the same time, your validation error is going to be very high. That's where we get overfitting. So what we have to do is we have to work on a point where we get both validation error and training error is very minimal. Okay. So when you have underfitting, and when you have the model is the when you have underfitting issues, and we have to keep on we have to increase we have to add the features in the data. You have to increase the number of parameters in the model. So to balance both bias and variance. In the case of overfitting, so since the model complexity is very high, so we can use some regularization techniques. So we'll discuss what is regularization in the next step. So we have been talking about overfitting issues in machine learning and deep learning models, and this can be addressed by regularization techniques. And the regularization techniques have there are many regularization techniques. One can use it to reduce the overfitting issues in machine learning and deep learning models. And there are four ways to reduce overfitting issues. One is L1, L2 regularization, data augmentation, and early stopping and dropout. So these are the four methods one can apply to reduce the overfitting issues. So overfitting, when we have overfitting issues, that model performs well on training data, but it fails on the new data. Okay. For example, I can say the R square for a particular model is going to be 0.99 for in the case of training data. In the case of train test data, it may be 0.80. So from that we can understand that this model is perfect. There are four, as we have seen, there are four ways to have regularization, and first one is the L1 regularization, and that is also called LASSO. LASSO is basically that is a short form of least absolute shrinkage and selection operators. So what we are trying to do here is we are trying to remove the unwanted features. Okay. So basically, in the machine learning model, we are trying to have the objective function is to minimize the loss. Okay. So and we are adding the penalty term, which contains lambda and the summation of weights. Okay, summation is overall absolute weights, okay. And that is called penalty term is ordered to the model loss function. And to when we have that when the weight is when the weight tends to zero, then what is happening? And we will be able to remove the unwanted features in the models. Okay, as long as you remove unwanted features in the model, and it will try to reduce the complexity of the model. So as a result, we can see there is not much of overfitting. So the idea is basically to have to remove the features. I mean, to remove the unwanted features in the model. Okay, that is the idea of idea of using L1 realization. So L1 realization, why we are saying L1 now? So we are adding the absolute values of all weights, and what if you have plus minus and all, this is going to be a positive one, and that helps to bring it to zero when we go for the gradient descent methods. When you apply derivative, and it is going to be zero. Okay, so that is the advantage of this. The key property I can say here is that derivative with respect to w, it is constant, and it pulls all the weights to zeros, and that's why that's the reason I can say the future the unwanted feature can be removed from the model. So in case of L2 recognition, where we use absolute value of weight, here we use squared up. So it is going to be it is smooth and parabola one. Okay, and where we use here you don't get zero, and it is going to be nearer to zero, I can say. So as it is here in L2 recognition, we can remove the unwanted feature. Here we can't remove the unwanted feature, but and we can remove the unwanted feature in L2 regulation. So when we apply L2 regulation and when we apply L2 regulation, these are most important things. Okay. See, we apply L1 regulation when we have a lot of features. Okay. So when you have a high features, I can say high dimensionality there. So when when there is a correlation between the features, and we can apply the L2 regulations. Okay, because that when you have correlation, it won't bring the weight value to zero when you go for the optimization. When we go for optimization technique. Okay. So these are two types of regulation. One is L1 regulation and L2 regulation. That is a basic difference. The application is different. Okay. The next one is the data accommodation. So data accommodation is whenever we have a small amount of data, we wanted to have a large amount of samples, we can go for data accumulations. So one way is basically we can apply the random transformations. One can if you have only one cat image, and what we can do is we can take it horizontally, vertically rotate and rotate at a different degree, and want to have a blur, bright, and noise. I can add noise, darker, and we can crop. So we can do many things with whatever the image we have. So when we have a large amount of samples, and that helps to helps to prevent the overfitting issues. Whenever we have insufficient data, then this will help us to add more data to the systems. Okay? So this is mostly used in the neural network models. And as I said earlier, we go for training and validation, and there are three ways we work on. And one is training data set, and validation data set, and another one is test data set. And training data set is basically for the model development of model, I can say. For the test data set, it is for the new instance. Validation data is for the whether the model can predict and whether we can model can predict exactly, and at the same time we can fine tune the hyperparameters over there. Okay, so the both the things will happen simultaneously. So where the loss has to be calculated for the each training and each epoch, and as long as we get the lowest loss in validation, we have to stop. Okay, so the point the point which has the lowest validation loss, we have to stop, and that will help us to reduce the overfitting issues in machine learning models. Okay. The dropout is basically deactivation of neurons, I can say. So when the model complexity is more, when you have a high number of hidden layers, or when you have a large number of neurons and hidden layers. Okay, so this is the completely covered. I mean the blue one is input layer, and the green one is the hidden layers. And when we go for when we see the model complexity is high, we can drop out certain neurons, okay, during the training phase with some probability. So it is going to be a random one. Okay, so when we go for dropout, I mean deactivation of certain neurons, this helps to prevent the overfitting issues in the model.